Well, I'm sitting with Mr. Henry du Preez, who's a consultant, an independent consultant with over 50 years of experience in the industry. And I think, Henry, I can't remember, but I know that we've known each other for a decade or two, but not for 52 years.
No.
Now, what sprung to mind when I met Henry the other day was to reflect on a couple of articles that he's written for the magazine Electricity and Control, and of course also for the Transformers and Substations Handbook, which we've discussed in a number of these face value sessions. But the two articles that sprung out for me was, the first one is partial discharge an issue, and the other one was the fundamentals of transformer design. And Henry, what I thought we'd do is to start off with a conversation about the role of an insulation system in what is in fact a very complex electrical device.
Yes, the insulation system itself not only sort of has an certain properties to deal with the temperature that you find in the transformer, the voltages that find in the transformer, and then the complexity of part of the winding is in the core, which is right up against the earth section of the winding, whereas the overhang itself is in air, or in the coolant that you have around the transformer, or around the motor, or the alternator, as the case may be. Part of the problem is, what a lot of people don't realize, is that insulation system is a capacitor. And you get a capacitive effect between the windings itself, and you get capacitive currents which flow.
So the capacitive current, just to make sure I understand, the capacitive current is that component of current which flows due to a fluctuation in the voltage levels.
Yes. And that flows between either the conductors itself or down to earth on the system itself. If the insulation is completely uniform, you get an even distribution of the voltage across the insulation. But now when you get into the overhang section, you don't have a uniform insulation system.
Right.
Your coils have a nice uniform insulation system, but then you have air in between, and you have blocking and certain other materials.
Right.
So you get a high voltage from time to time, depending on the spacing of the coils in the overhang, which give you a higher voltage across the air gap itself, where then partial discharges can take, if that voltage is high enough to break down.
So that's right. So now you get a very non-linear voltage gradient, and you then start initiating a discharge effect in the air. And why do we call it a partial discharge?
Because it's not there, and it's only in certain areas in the motor itself. If you look at the article, you'll see there's a photograph here of a winding where we had partial discharges in the slot, but you'll see some of the coils there have been eaten away. The insulation has been eaten away.
That's very clear. That's very, very clear. Yeah.
But the ones that are close to the earth potential, the star connection, don't suffer the same amount of damage.
Let's take this conversation a little bit further. So this is the July edition, and in fact the photographs are quite spectacular.
Yes.
Did you take those?
Yes, I took all these photographs on that.
Now this looks very interesting to me, because what we see here is the sort of the end of life, effectively, of an insulation system. So how do we stop that actually happening? What do we do?
I don't think you can stop it completely. There are certain things that you do in the insulation system to reduce it or to prevent it. One is you try to make sure your overhang section, the coils are spaced equally distance apart, and that you have a minimum gap between that. Because if that gap changes and becomes small, then you have a greater chance of partial discharges. In your slot section, of course, you have a corona shield over the coil, which is in conductive tape over that, which makes a good connection with the earth and with the coil itself, the insulation on the outside of the coil. Because your core is never perfectly uniform all over. So if you didn't have that, you're going to have some air voids in place.
And so that effectively gets rid of the possibility for exceptionally high voltages at any particular point in that insulation system.
The two first photographs that we have there on, other than the coil itself, is motor that's actually an alternator that's been in service for close on 30 years.
Wow.
So I accept the damage that's done there.
Of course.
It was repaired and rewound so that they didn't have a a fault occur when they didn't at least expect it. The other photographs that we got there are actually very short life, and basically my interpretation of this is the coils were badly formed and the gap between the coils weren't uniform.
So the stresses were
excessively high. And in a matter of a few years, so these are only a couple of years old, you can see how much damage was done in the coil at that particular stage.
So now, let's just take this back a little bit and understand. So what this tells me, though, of course, is that partial discharge, as you've said, you can try and limit the partial discharge activity, but you're not going to eliminate it.
No.
This implies, of course, that you can monitor it
Yes.
and watch its progression over time. Let's talk through that process. What does it tell us when we're monitoring partial discharge activity?
When you're monitoring, and monitoring partial discharge, there's no absolute values and say what must the partial discharge be on a particular motor, because all motors are different. You've got different capacitances in the motor, and you can have different currents in there. But we do tend to monitor it, and we have a guide. Now, if you can monitor it over a period of time, or you can check it every 6 months, every year or something like that, you can see if there's any decay or any increase. And if there's an increase in the partial discharge, you know that the insulation is now beginning to deteriorate.
It becomes a comparative measurement.
Yes,
Henry, you mentioned 6 months to a year. What is logical, and does it depend on the kind of machine, the value of the machine?
It depends on whether the machine is critical or something like that. I mean, if that particular machine happens to be on an oil rig, now you haven't got spares, you can't put a spare on there. It's extremely difficult to take the machine out. It's sitting in the middle of the Atlantic, so you have a problem. So there you could look at possibly say it's worth doing a continuous partial discharge measurement.
So an online system monitoring it
continuously. Or you can say, I want to monitor it every 3 months. I'll go in, I'll put in some capacitors, coupling capacitors or something like that, to be able to monitor the discharges that are taking place. Periodically, you can go in and plug a unit in, take some measurements. You don't have to isolate the unit or switch it off or something like that, and you can remove it. If you do a low frequency partial discharge measurement, though, you can't compare it with an online
the actual operating
conditions and that type. So my view is rather to put in couplers and then do at operating frequency,
and effectively
50 or 60 hertz.
What you'd be doing is you'd actually be monitoring the charge flow from the coupling cap into the discharge itself. And then you would interpret that as being indicative of the...
You measure it either in coulombs or in voltage. Normally.
Then one other thing, and I think that we've had a good conversation so far, but the other thing that struck me about your article was that you actually explicitly talk about PWM converters, we're talking about power electronics, and the new sort of way of controlling and driving motors. What is the impact of that now going to be in terms of our monitoring and the influence of that supply on partial discharge activity, if any?
Yes, the article that I'm trying to cover there is that we are getting partial discharges because you're getting extremely high voltages, but short pulses, depending on the inverter, the inverter supply. The technique nowadays is to use IGBTs, which has got a very fast switch.
Very rapid switch, incredibly rapid switch.
The switching time is now critical, combined with the cable length that we have on feeding the motor. If your rise time and your pulse is slower, then you get a reflection at the motor or the machine, and if you get that reflection, of course, you have high voltages or multiple voltages on from the system itself. And the new IEC specification 60034 -42 41 and 42 18
18-41 42.
They tell you under severe conditions and benign conditions what you can expect, say on a 500 volt motor, and they're talking of peaks of up to 4,600 volts. And remember, this is repetitive peaks. It's not once off.
That's right.
It keeps on there all the time, so it shortens the life of that. Partial discharges are not going to destroy a machine, either the medium voltage machines or the low voltage machines. As soon as you switch it on, it's going to shorten the life of the machine. It brings
Right.
the failure
I
rate
understand it.
forward. And that's the critical
And I think
point.
the key point, and just to make sure that everybody appreciates that, instead of having a nice pure sinusoidal supply, effectively what you're doing is you're smacking in pulses of voltage at higher than the peak value of the sine wave to effectively recreate the sine wave form using pulse width modulation. Now that's actually quite an interesting observation, because I must be frank, it's not something I'd ever thought about. And of course it's going to have a big influence.
Yes.
And therefore, as you point out, you've got the new standards which actually deal with this,
Yes.
which we need to now become cognizant of and appreciate the risk we run.
And that only came out in March this year.
So it's brand new.
It's brand new.
Brand new.
And we also got to look at the repair industries and things like that when they repair motors. One of the biggest problems, of course, is we say insulate a low voltage motor with inverter grade wire, which has got
Yes.
a mica in it, which is but now
And mica
you go
being
to
an insulating
insulating, which is not damaged easily by
Right.
partial discharges. But the mines and industry and all that have hundreds of motors in, so they've got spares in the store,
That's right.
and some of them have got inverters on, some haven't. Now, do you insulate all your motors for inverter grade, or do you?
I mean, practically, I'm running a large mine. I've got a big installed base of motors. Now I'm going for speed control, new converters. What do you advise
Yes.
these guys? What do you advise them to do?
Inverter grade wire is more expensive,
Okay.
and it's not universally, it's not that easily available as
Right.
the standard wires that we've got. But the other thing about the repairs and industry and that is, if you look at photograph or figure 7, you'll see that sometimes
Wow.
the winders get wires crossing each other, and of course then
Actually a beautiful
even
picture.
more susceptible.
That's right.
Because you now get high voltage
Between turns,
between
actually between
turns.
turns.
Normally, because random wire wound machines, they are random, and some of the
That's right.
turns get very close to the other turns, the higher
So you can
voltage
get quite
turns. So you can get
exceptional
quite exceptional.
interturn voltages.
And that is a particularly bad example. But you can see some others in some of the other photos. I see quite a number of these when I go from repairer to repairer.
Right.
And some of the repairers do very, very nice jobs, I must admit.
Absolutely. Henry, thank you very much. It's been a pleasure to chat.
Thank you.